thank you all for spending your evening listening to a talk about plastics. It's really a privilege for me to be invited here, and I must admit I'm quite nervous, and that's why I decided to talk in English, so I'll try not to make too many mistakes in my mother tongue. But plastic is an amazing material. We have a love-hate relationship with it. And I think sometimes we forget how many good things it's brought to our lives since the Second World War. Andreas Mogenson's spacesuit here is very similar to the Apollo spacesuits of the 60s and 70s in that it contains around 22 different kinds of plastic. And without these materials, there wouldn't have been so many explorations of space. We also have plastic in our daily lives that we set a store price, I'm mixing my languages, that we really appreciate. For example, all our credit cards, our ISA cords, they're all plastic. Many of our toys, perhaps there we are not always so happy about them being plastic, but Lego bricks, we're really proud about the development of those in Denmark, and they're made out of plastic. And then we have the other side, plastic pollution, that we're not happy about. And unfortunately, here we see in this corona times, we have far more plastic gloves, face masks that are just thrown out onto the streets. And we talk about plastic lasts forever, but what we're going to discuss this evening is that really true? So I'll begin by saying that what I understand about plastics to be from a chemist's point of view, because that is my background. Why do they break down? What makes them break down? How long does it take? And what do we mean by breakdown or deterioration? And then, as Karen said, I'm still involved in quite a new project called Marine Plastic. That's one of the projects that I'm involved in. But how can we transfer what we know from plastics and cultural heritage, which is the area that I've worked most in, how can we transfer that to understand much better plastics after their use, post-consumer use, as pollution? And how can that knowledge also help us understand how we could find a solution to some of these issues? So if I start with what are plastics, chemically speaking? They're giant molecules, they're polymers, macromolecules is another word. They can either be made from a start material of oil, or coal, or wood, fossil materials that are not sustainable, or the same materials can be made from sustainable sources like biomass, plants, fungi, enzymes. Just because they're bioplastics made from a sustainable source does not necessarily mean they're biodegradable. You can make identically chemically similar materials from either oil or plants, and they will have the same chemical properties. Around 4 to 6% of our oil goes into making plastic, so we could say that's not a huge amount in the great scheme of things, but still, it is an amount. The rest goes to make petrol and chemicals. But just a polymer alone is not a plastic. To define it as a plastic, it has to have additives, it has to have something to stop it degrading. Even it needs thermal stabilizers so that we can mold it into a shape. Without that, it would just degrade. It sometimes needs softeners or plasticizers. It very often needs filling materials, coloring agents, perfumes, etc. And the final definition of a plastic is that it's a material that can be shaped in a mold or rolled out into films, or air or nitrogen can be pumped into it to make a foam. And that is why I don't consider materials like paints to be plastic. They might have a plastic basis, and I know that in Danish we say plasmaling, but it isn't actually a plastic if we follow the traditional definitions. And nor are natural polymers like paper and wood. We can't mold them, we can shape them, but they can't be formed in the same way that synthetic plastic can be. If we look at the production from 1950, most of the plastics that we have today were first developed just before the Second World War or just after. And you can see here the enormous growth from 1950s to today. You can also see here the little green line, which is the bio-based plastics, and that's only around 0.45%. There are very little bioplastics today that are produced. And that's not because we don't have the technology, that's mostly based on the economy, because oil is relatively cheap. So we will have the ability when the oil runs out, but still. Another thing that this graph shows is the big change with production in Europe to production worldwide. So most of the plastics that are produced today are not produced in Europe anymore. It's much cheaper to produce things in India and China and in Asia because they're various reasons, but their salaries are not as high as in Europe. And that's both a good thing and a bad thing. It means that we've lost in Europe a lot of the technological knowledge about plastics. But if we go back a step and say, when was the first plastic developed? That was actually around 1862. And the plastic that was produced then was kind of found as a replacement for billiard balls, of all strange things. American rich gentlemen had plenty of time and their favourite hobby was playing pool or billiards. But those balls were made out of ivory and there were nearly no elephants left in India or Africa. So a rich man put up a reward for someone who could make a synthetic billiard ball so that he could and his friends could continue to play billiards but without killing elephants. And the material that was found was by accident mixing paper fibres with acid, with nitric acid, and what they made was cellulose nitrate or cellulose acetate, as we call it really. The first things that this wonder material was used for were all kind of imitations of ivory or tortoiseshell. So the hair comb up on the left there looks very much like tortoiseshell. The one on the left is tortoiseshell, but the one on the right is actually cellulose nitrate. We also made things then like dolls. I mean, dolls were not the soft, cuddly things that children play with today. They were actually originally made out of ceramic and they were hard. So it was natural to produce them again with cellulose nitrate. Film base was the biggest use. It replaced glass as a material. But it had one huge negative, this wonder material, and that was that it was highly flammable, because actually it was very similar chemically to gun cotton, or what used to be used in guns before we had bullets. Today, the main use of cellulose nitrate commercially is nail polish. So it's a warning, don't smoke your cigarette while you're painting your nails, because it will burn very rapidly. So the film industry, that was a serious problem for in cinemas, that cinemas burnt down because there was so much cellulose nitrate film. So a safety film was developed called cellulose acetate in the 1920s. And this is an interesting material because just like cellulose nitrate, it's based on cellulose or paper. And so actually it's a bioplastic. Its source material is sustainable. And cellulose acetate is not flammable. It was used until 1969 as a Lego brick material, but the problem is that it shrunk, as did the animation Disney films, the original cells. So that was also a negative. So Lego bricks today are made out of a very modern plastic called ABS that our computers are made out of. Cellulose acetate is made out of taking paper. You don't actually directly treat it with acetic acid, but effectively that's what you do. You have to add some plasticizer to it to make it soften, and you have to add a fire retardant. Now, I've wondered for many years why you need a fire retardant for something which is called safety film. But it's actually because the cellulose acetate can't burn, but the plasticizer can. So this is the reason why it's been added. Today, global production, well, you can see that it's just a fraction of ordinary fossil-based plastics that's produced. But still, more than 800,000 tonnes a year isn't just nothing. And its biggest application is cigarette filters. Also, fibres and textiles like viscose, sellotape, The base of the sellotape, not the adhesive, is cellulose acetate, and spectacle frames. And it's interesting that opticians advertise madly that you can have the new acetate frames. They're not really so new, they're from the 20s originally. But the first real synthetic plastic was Bakelite, a chemically phenol formaldehyde. And this was 1908 or 1904, depending on which books you read, whether they're German, American, or British. They all claim to have made the first Bakelite. But Bakelite is still a wonderful material. It doesn't cause us many problems in the museum because it doesn't degrade. It's a wonderful sound insulator and electrical insulator. But the big negative is it comes in just black or dark brown or dark red, and especially after the First World War, people did not want something heavy and depressing looking in their houses, so it lost popularity. All the plastics that we have today since the Second World War, with the exception perhaps of cellulose acetate and cellulose nitrate, but they're a very tiny part of the market today, are made in another way. We don't take a natural material and treat it so that we can mould it as we did then. We take a very small unit called a monomer, which could be a gas or a liquid, very low molecular weight, and break these double bonds in the monomer so that they open up, and now we can join lots of those monomers together to make a polymer, a very high molecular weight material. When you increase the number, you change the phase from being a gas or a liquid to something, a solid, which a plastic is. The plastic needs then to have the additives added to it. If it needs a plasticizer, it's added at that point. Any anti-aging additives, lubricants, and colour. The lubricant is added because it's a bit like making a cake. If you heat up your plastic without having a lubricant, how will you get it out of the metal mould? So those are waxes that just that migrate to the surface and mean that we can make our Lego brick come out of the mould. All these additives, they sit between the polymer chains. So the polymer chains, I remember being taught, I think at school or perhaps university, that polymer chains are a bit like spaghetti. They're very long chains. They don't have to be just linear, they can have branches in them, but they basically are long chains. And if you think about spaghetti, if you cook a pan of spaghetti and then you let it cool, all the chains sit together and make a horrible starchy mess which isn't tasty. If you then add oil, that's a bit like adding plasticizer to your spaghetti, because now the chains flow over each other and you can have a more flexible plastic. Because most of the plastics that we have today are made away from Europe, the liquid polymer is dried down and the additives are added to it, and we end up with what's called granulate. We call it granulate. It's like a wannabe plastic. It has all the ingredients to be a plastic. And then we can extrude it or mould it. In the environment, when we find these things, what we call them microplastics, because they're primary microplastics. And if they're found in nature, they're not from degradation of plastics. They're because they've been dumped or as a result of an accident. But a microplastic just means something that's a particle that's half a centimetre or smaller in diameter. It could be a fibre or it could be granulate. We'll come back to that. So all the polymers that we have today are made in this way, by having monomers that are joined together. They can be more than one monomer joined together in the same plastic, and they have different properties. So these are ones that we know: polyethylene, carrier bags. We know PVC very well for various reasons. We're not very happy about PVC in the environment, but it's been a godsend for things like blood bags, for example, couldn't be made of anything else apart from PVC, so we're pretty happy with it sometimes. Polystyrene, polypropylene. And cola bottles or soda bottles are made out of polyethylene terephthalate that we call polyester. That's a great material because it's a barrier to gas. Without having that, that property, we would have flat cola all the time. If we used polyethylene, which is very good for Tupperware containers, that lets gases through. So we have to have a good range of plastics to have all the properties that we need for food use, for foams. They each have a use. This is a sort of display of all the plastics that we know and love today, and they have different properties and different applications. 40% of the plastics produced have an average lifetime of about 15 minutes, and that's because they're used for single-use food packaging. That's something that's going to change from next year, because from the beginning of January next year, the EU have forbidden single-use plastics. Not all of them, but that percentage will change, because we won't be allowed to produce them. There are other plastics that are used for a long time, like Teflon as coatings, and ABS, that's a hard plastic, but it has some flexibility, that's used for computer screens. What about our love-hate relationship with plastics? There are many sayings or citations about plastics, but I thought these two are quite funny. One is by Michael Jackson, who said, "I love realism, I don't like plastics." I presume he wasn't talking about plastic surgery at that point, but anyway. Another one is one that can be interpreted in many ways. Biefer and Zagragan, some German artists, they said plastic artifacts will be the most important witnesses to our time. Now, that has different connotations. When they wrote it in '91, there wasn't so much discussion about plastics in the environment as there are today. And I think they actually were talking about museum objects and artworks and as something positive. But of course, the National Museum has a good collection of different kinds of plastic. And I've just taken a few examples here of the spectrum and why they should be saved, because this is really why I started as a chemist in museums, because there was a huge concern at the beginning of the 90s that plastics would not last very long in our collections, and it was the first time that it had been appreciated, and there was panic. You can see here the cellulose nitrate spectacles. They haven't lasted. They probably, after around 20 years, they probably began to degrade. Lego bricks have lasted in their design, but not in their material. Cellulose acetate stopped being used at the end of the 60s. In the 1970s, we had a lot of plastic clothing. We had a lot of plastic replacement. PVC replaced leather in car seating and also in upholstery and in clothes. Now, we can discuss whether this is a very tasteful example, but it's something we have at the National Museum that we preserve. Of course, plastics have also been used to commemorate events. Now, this in 2015, there was the terrorist attack in Krutton in Copenhagen, and Finn Nørgaard was murdered. And afterwards, amongst the bouquets and the flowers, the traditional ways to mark an event, a sad event, these perleplater, these beads, iron-on beads, were found with Finn written on them and collected by the museum. Another happier event in 2015 was that Andreas Mogensen took his first exploration, and his suit is on display in the National Museum at the moment. 2018, another happy event was that the metro in Copenhagen seriously began to be built, and artists were invited to decorate the hoardings for 6 months at a time. There was one artist that chose to use vinyl records as part of his design and paint an eye around them. Today we have many possibilities with plastic, both good and bad. We're happy to have plastic fillings in our teeth that are white. We're not so happy to have these single-use plastics, especially at the moment, that are just discarded after use. Artists have always used plastics, well, really seriously since the beginning of the 80s, but many of them find it very difficult to understand the properties. So PVC, Thomas Saraceno has used inflatable. PVC is excellent as an inflatable material because it holds its air, but when you put water in it and try and grow plants on it, that's not so good. It becomes cloudy because the plasticizer migrates out. Bjørn Poulsen, he's chosen a very stable plastic, melamine formaldehyde, margrethe. He takes them home from IKEA and takes an axe and chops them up. And then he doesn't use a glue, which is clever because it's difficult to stick plastics. He uses nuts and bolts to screw them together again and make something new. Christian Flint, he is an artist and a designer, and we had a project, I think it was, I can't remember when exactly it was now, but I think it was before 2016 because this is the old laboratory, and I had a workshop to invite artists to find out how what analytical equipment could do in relation to plastics, and I invited him to bring a small sample for infrared spectroscopy, and he came with this garden bench that was 1 metre long and said, is this enough? What's funny is that you need something about the size of a pencil head to run infrared spectroscopy. But what he was interested to find out was that the polyurethane foam that he'd chosen for his bench was actually a disaster material. It was going to be out in a garden, and I estimate within about 3 months it would be yellow. But the big question that we all ask is, how long do plastics last? Now, if you Google, this as I have here, you can find a whole range of different values. Plastic bags, 200 to 1,000 years. Ooh. Wellington boots, rubber boots, 50 to 80 years. Plastic styrofoam cups, 50 years. But then you can also look on another homepage and find out that balloons, which are rubber, natural rubber, they might never ever degrade. That's a big variation. You can usually find in tiny print there that they tell you these are based on predictions or modelling. But the difficulty for me is when I look at this data is, what does degradation mean? When is the end point? I think in museums we have, and cultural heritage, we have a definition that loosely is based on a loss of the original significance of the material, not just its material properties, but also its significance and interpretation. When we buy a product from the supermarket, we expect it to last, and then we say degradation is when we can't use it anymore, and it's still within the guarantee period. So we don't keep things forever, or sometimes I'd like to at home, but I'm not allowed to, and that's fair enough. But there should be a function associated with product use, and that's tested. So these gloves have never been used. They're rubber gloves, but they have big cracks here. And I would be in my right to go back to the supermarket and say, I haven't used these and they've degraded. That's product use. But then there's another area, which is a loss of the physical integrity. Something crumbles or fragments to microplastics. Microplastic, as I said, is just a particle that's less than 0.5 centimetre in diameter. And really, we don't have any data for that. We're estimating. We don't have any measurements because the first plastic was 70 years ago, real synthetic plastics. But the first microplastic was discovered in 2004. So these estimates of hundreds and thousands of years, they don't really fit with our reality. Degradation is, as I say, we need to define it, but when plastics when we see their degradation, that means the additives that are protecting them have run out. And what we're trying to do in conservation is prolong that period as much as possible by keeping things in the cold or the dark, which is great for us in conservation. But if you want to exhibit a plastic object, it's not so convenient to take someone down to the freezer and say, you can look at it here, it's -20 centigrade, or in the pitch black. That induction period, you might think that's weird, but it's like putting sun cream on when you go to the beach. You know that it will last for, I don't know, an hour depending on the factor, or 2 hours, and then you're going to find you're going to get burnt. That's the same that additives do. They try and protect the polymer. But the plastics industry, they can't wait. Suppose we bought some waders and expected them to last for 20 years. They can't wait 20 years to find out if they've lasted. So what they try and do is they put energy into the system. They heat up the plastic or expose it to a lot of light and try and predict within a convenient period how long they last. So something like if you have a material that degrades within, say, nearly a year at room temperature, if you want to speed that up, you can heat it to 60 centigrade, and then you can have a result within 4 weeks, which is much more convenient. The big question is it the same reaction that happens at room temperature? So to go back to what are the causes of degradation, we can generally divide them into physical and chemical causes. Use is the main physical cause. Then you can also have movement of the additives. There could be either Tupperware containers are really good at absorbing tomato colour, for example, or curry colour. That's what we in the museum would consider degradation. It can also be loss of additives. So here's an example. This is a polyethylene, something like a Tupperware box that's been used to store fishing lures, which are made out of PVC. Lures contain a very high percentage of plasticizer. The polyethylene container contains no plasticizer, so by diffusion, the plasticizer moves from the lure into the plastic. It looks very pretty, but it's not super functional as a box anymore. It's rather soft at the bottom. Why does that happen? Why does the plasticizer move? Well, because it's not chemically bound. Very few of the additives in plastics are chemically bound. They're just physically sitting there. And so the bonds are very weak. And they move out with time. It's a bit like if you have a washing up sponge, a dry one, you put it in the washing up water and take it out, all the holes are full of water. If you then squeeze it, you're mimicking degradation where the polymer chains are packing together. And now the water or the additives migrate out. What about the chemical cause of deterioration? We can divide them into two categories. Some plastics are very vulnerable to reaction with air, with oxygen, and other plastics are very vulnerable to reacting with water. So cola bottles, they react mostly with water and they're not so affected by oxygen, but Tupperware containers, polyethylene, they react with air. If there's a metal present, that can also speed up degradation, and that's a big factor in the environment, in the marine environment, where there are metals in the water, so that could be a big factor in deciding how long plastics take to break down. When I was at the British Museum, I realised that I was a lowly civil servant. I could be there the rest of my life earning very low salary. And when I heard about that Charles and Di were going to get married, I thought, this is my chance to make $1 million. I'm going to invest in souvenirs. So I bought boxes and bags of balloons to celebrate the day, which was 1981. Yeah, by 1990, my investment was worth zero because they had all oxidized. Of course they had, because natural rubber or synthetic rubber is a very, very poor quality plastic, and it reacts very quickly with air. In the same material in a rubber tire is vulcanized. That means sulfur is added, so it's much more resistant. Hydrolysis. That is also a problem, but that happens rather more slowly. Cellulose acetate and cellulose nitrate are two of the plastics that react with water. They can also be called a malignant plastic because they don't just sort of sit there quietly and degrade away like the rubber balloons. They give out an acid, and that affects all the materials around them. So these cellulose acetate cutlery, it actually looks exactly like mother of pearl. And one of our colleagues, he brought them many years ago after Easter because his family this was a special set and they kept them only for Easter and Christmas. But one time when they took them out, they thought the mother of pearl didn't look so great. And what's happened here is that this cellulose acetate has given out acid and it's actually degraded back to paper again. So cellulose acetate, I said it was a bioplastic, and when it degrades, it goes back to its roots. It goes back to being paper again. But unfortunately, it produces this acid, acetic acid, which is vinegar, and it has, when this reaction happens with photographic film, it's called the Vinegar Syndrome because you get that vinegar smell to identify it. Usually you get a mixture of both the physical and the chemical. It's difficult to differentiate. The Apollo spacesuits, and actually Andreas Mogenson's spacesuit also, has some tubes that carry air and water to a backpack. Those tubes are PVC because that's a really good material to carry water and oxygen. And unfortunately it degrades. the additives in it migrate out, the plasticizer, and then the polymer breaks down. So today those tubes are not in the Apollo suits. I haven't looked at Andreas Svensson's suit, but they were transparent and flexible, and today they're brown and like glass with crystals of plasticizer on the surface. So we go back to the question, how long do plastics last? And can we actually compare these predictions and modelling with from accelerated aging with real time? And this is where I think I'm excited. This is part of the research that I'm doing now, because in the museum what we're doing is we're keeping things for a much longer time than their sort of product lifetime or even their expected lifetime. We're trying to keep them alive for future generations. So that's real-time aging. What industry are doing and what we're doing when we do research and try to speed up the process is accelerated aging. I've had a project with Stadtmuseum für Kunst looking at Klaus Carstenson's artworks. This is one called Eterlehm, which he made in the 80s. At that time, he apparently lived, or he walked past a furniture factory where they were making seat cushions, which were round, and the offcuts were thrown into a skip container. He collected them, stapled them to a canvas, painted the canvas, apparently urinated over them also, and by, I think after about 10 years, there was severe degradation on those polyurethane foams. I mean, it's a bit like washing up sponges, very poor quality foam that degrades by reacting with air. The good thing was now the conservator at Stadtmuseum für Kunst, Louise Cohn, she's been trying to investigate the possibilities for conserving this. And they're so degraded, there was really no possibility to consolidate them, try to stick them or reinforce them. So we did some accelerated aging to see if we could make some copies of that degraded foam. So we used accelerated aging. We have some new foam on the left, some heat age foam. We use some 60 or 70 degrees centigrade because that's what you use if you do medical testing on plastic materials. And expose them to sunlight. And we were allowed to take small samples from the artwork as well. And what we can see here is that the new foam, the cells on the new foam, this is around 200 times magnification. As you can see, they're in good condition. When you do heat aging, they're slightly degraded. They're extremely degraded, and the foam has developed in crumbs. It's just fragmented. With light aging, and when we look at a sample of the real object, it's much more similar to heat aging than light aging. So we know that we've done some overkill with the accelerated aging. I'm transferring that information to the marine environment at the moment because I'm in a project called Marine Plastic together with RUC and Aarhus University and DTU and Aalborg University, and our part of it is to look at this question of how long does plastic litter take to degrade down to microplastics, because microplastics are a huge concern at the moment. They're small particles that can be eaten by fish, they can be taken in by the gills of animals. Nearly all creatures seem to have them in them at the moment. But we don't know how harmful they are. Luckily, that's not my part, that's DTU's part of the project, because that's a really complicated thing to investigate. The other question is, can all kinds of plastic, there are around 50 different types of plastic, can they all form microplastics? Not all plastics have been found in microplastic form as yet. And of course, which environments promote the formation of microplastics? That's very important too, because maybe we can find some areas of the marine environment where plastics don't degrade to microplastics. That would be great. So we've taken a broad range of the plastics that we find today, like polystyrene coffee cups and nylon strips, PVC tubing, cola bottles, tyres, washing up sponges, and some new generation, some bioplastics. The main one that's commercially available today that we use a lot is called polylactic acid, and that's made from sugarcane, from either by fermenting it or by treating the sugarcane, extracting the sugar and making monomers and polymerizing them. But it's a plastic which is also biodegradable, and that's why it's interesting. So we've done some accelerated thermal aging to try and compare accelerated aging and real-time aging. And we can see that after a very short time, we're getting degradation of most of the plastics. This is an example of PVC. And you can see it's beginning to look a bit like the Apollo spacesuits already after a few months. So it's extreme. We have some samples exposed to the Danish weather so that we can have a real picture of rain and if we ever get any sun, freezing temperatures, if that affects the plastics. And they're exposed, it's a standard, they're at an angle of 60 degrees to the sky. So those have been exposed for a year now, but after 6 months already we could see the main plastic affected was washing up sponges, polyurethane foam. We have some analytical, as well as, actually your eye is a very good indicator of degradation of plastics. It's actually more sensitive than some of the analytical techniques we have. But one that we do use is infrared spectroscopy. We need a very small sample for it, so we can use it on applied to objects. We can't take big samples, and it's also very sensitive. And it's helping answer some of the quite basic questions about plastics, like does daylight degrade plastics, or is it just sunlight? Is daylight more harsh? Does it degrade plastics faster than warming them up? And here we can see the infrared spectrum gives an indication of mostly of the polymer, of its chemical background, chemical structure. We can see that a new chemical group has been developed here when this plastic polystyrene cup has been exposed to sunlight after a year. But it hasn't developed in heat, even though the equivalent heat is 10 years, the light was only for 1 year. So we can say that light is a serious problem, especially ultraviolet light, to plastics. Another basic question is, what about the colour of plastics? Well, at the moment we're just looking at transparent or white and black. But the early indications, we can calculate something called the oxidation index or degradation index. The larger the number, the more degraded the material. And our initial results suggest that transparent materials are much more sensitive to degradation than darker materials or coloured materials. We've taken the samples and threaded them on ropes and put them in our underwater site in Lunes. I'm so lucky because I'm not afraid of water, but I wouldn't dive down to the bottom of, a pond, I don't think. But I have wonderful colleagues in our department who have great expertise with this. So David Gregory, sitting here, and Henning Mathisen, they have been involved in putting some of these samples under the water in Lunes. So there's two techniques that we've used. We've threaded the samples on ropes and put them on a frame and put those under the water. Of course, we protected them with some net because if they should degrade to microplastics, we don't want to pollute the surrounding waters. And then we've made this kebab with different plastics on it and shot it down into the sediment. That wasn't easy, as David tells me. But here they've been under the water. The frames have been under the water here, and the samples have been put in the sediment here. So after 12 months, Henning and David went to, I have to use the mouse, sorry, to collect them, and I'll just show you I'm taking them up after 1 year. There's no sound because apparently there was a lot of bad language in the background, so I took them up, and the initial thought was there was no degradation because the netting had protected them. If I just move ahead here. clearly there's a lot of growth on these samples, even though they've been protected by a net and a mesh. But after, I think, 12 months, they look completely different to how they did when they were put down. They actually look, I think, very beautiful. They've all kinds of barnacles, and we had to separate some muscles from them. They're completely coated. What's interesting is the deeper down they were, the more protected, the less growth they have on them. So these were 128 centimetres, just over a metre under the water, and this was just less than a metre. But the difference is amazing. We have all the different kinds here. Polystyrene cup that was transparent, black polypropylene salad boxes, polyurethane sponge, cappuccino lids. The samples that were shot into the sediment have also produced interesting results, because after the same period of time, the ones that were actually in the sediment show nearly no degradation. They look totally new. But the ones that were just stuck up, it was quite a difficult process to have these down so deep in hard sediment, they have a little bit of growth. So what can we say? Well, generally, the more oxygen that the plastics have been exposed to, and the more light they've been exposed to, the more biogrowth they have. Now, at the moment, I'm just starting on the analysis, so I don't know if there are other degradation signs underneath, but certainly there's some biogrowth on them. Can compare this. We've known in the museum for many years that light, especially ultraviolet light, degrades plastics and other organic materials. This is a pair of rubber shooting gloves from the War Museum, as it's called now. The glove, they're from the same pair from 1947, but the one on the left has never been used and has sat in a dark box with a little bit of oxygen, of course, but no light for many years. But its partner has been both used and exhibited and had light and oxygen, and it shows clear signs of increasing oxidation. So the two things fit together. So we can agree that research into conservation, degradation of plastic objects can certainly contribute to our understanding, and it will, I hope, of what happens in the marine environment and when plastics are waste. But I'd just like to round off with something that is positive about doing something about this issue. The Marine Plastic Project was a partner in the mass experiment last year, where 57,000 school children in a 2-week period in October went round and collected plastics in the whole of Denmark. It's actually the first national survey of plastics pollution in any country, and we've just published it in scientific reports. The results, they had simple tools to identify the kind of plastics, and they divided them into 22 categories. Well, cigarette butts was the biggest category, and it actually occupied almost a third of all the plastic rubbish in Denmark on streets.
And it's by number?
It's by number.
Not weight?
No, we can, you're right. Well, there's many ways to divide pollution, but this was done by number. Quite right. Thank you. Plastic carrier bags, they were also a considerable contribution, but not as bad, and I think that's partly because we pay a deposit. We pay for plastic bags in Denmark. Bad was sweet wrappers, crisp wrappers, and balloons. I hadn't thought about that. But because cigarette butts was the biggest source, I thought that was worth further investigation, because, as I said a while ago, cigarette butts, the filter of the cigarette, which is what we call cigarette butts, is cellulose acetate. And that's a plastic that we know very well from museums and from conservation and objects. So there's around 8 million cigarette butts on any one day in Denmark. And København's Kommune say that it costs 2 kroner per butt to pick them up, because they have to pick them up individually. So this is a really expensive problem. The other problem is that they contain water-soluble toxins. They don't contain heavy metals, actually, because those are not water-soluble. And actually, they're not taken up by the filter, which is another discussion about how effective cigarette filters are. So if we cut a cigarette filter open, we see thousands of tiny cellulose acetate fibres. Research suggests that they last, if we don't do anything, if we don't collect them up, they'd probably last, maybe up to 3 years, or at least 3 years on a pavement, a dry pavement. But if it rains, that shortens their lifetime to about a year. And if they're thrown into water, that's also something. Compared with other sort of street pollutants, something like chewing gum, 5 years. A plastic bag, we're back to that 400 years. It sounds like a very long time to me. But we know how cellulose acetate deteriorates, and one of the things that speeds up its deterioration is acid, because it's a reaction, reacts with water, but it's speeded up by acids and alkalines. So I thought that might be an interesting project, and it's been made into a school project, which is just started actually. If we compared how long cellulose acetate butts took to degrade in different environments. I'm really happy that St. Levard Knut School in Lyngby have agreed and have started in this project. Even though Corona has tried to stop us, they were supposed to use the museum laboratory, but they were happy for us me to come to their school laboratory. And so what we've done is we've put some cigarette butts in air and soil, and we've made some synthetic seawater. I thought it would be fun. An acid, a lemon. Organic lemons are actually more acidic than ones with pesticide on them. So we've cut lemons open and pushed some cigarette butts into them, tap water, soapy water, and a freezer and oven. And now we've been measuring the length of them for the last few weeks. And the very initial results, I must say, but the lemon actually is doing quite well. We also tried some vinegar, and it looks as if it shrinks the butts. So this is initial results, but exciting that we could actually have some influence perhaps on how long it takes cigarette butts to last. So I'll just conclude by saying there's no such thing as a plastic that lasts forever. You might hear about it, that, oh, we're going to develop some plastics. No, we can't, because of their chemical structure. But it's really important to understand in different environments and different applications how long plastics do take to break down, because they do, and what's the main causes. Because museums try and keep everything, not forever, but we say to the next generation, or at least 50 years, we have a lot of experience of plastics, for good and bad. And so we're a source of information and actually of materials. And this, I'm planning now, I've just taken on this new position, and my hope is to continue the work of applying our knowledge of plastics degradation into the environment, and also maybe into how we can take on this circular economy challenge that we have to try and recycle plastics more and put them into a better use and a better perspective. I'll just finish by showing, plastics in the marine environment is not a good thing, but actually we found when we took our plastics up, we had to throw some fish. Well, we didn't kill them, but we made them homeless. And this is a polystyrene cup which is totally covered in barnacles and creatures which are actually making quite a good use out of the plastics. But I'm grateful for funding to the Velex Foundation and the Croair Fund, and thank you for your attention, patience.